afternoon, everyone. So today we will study switch reluctance motor or variable reluctance motor. Okay, so these are special type of motors which works by the when we switch the current when there is a change in reluctance or the change in inductance. Okay, so it is also known as variable reluctance. Okay, so this is the first option. Description details of these switch reluctance motor. So there are generally two types of switch reluctance motor: single salient and double salient. Okay, so this is two phase, phase A and phase B, and this is two pole motor. Okay, so so in single salient, the rotor or in doubly salient motor, rotor have no windings. So it is plain stack pole. Okay. So this and here it is in single salient it is long salient stator, and in case of doubly salient it has got salient poles. Okay. And windings are connected. This is A dash, A dash. So we first form here and then it comes to here like this. Okay, so similarly, windings will be connected in phase B also. So these are two types of variable reluctance motor: single salient construction. Okay. So this cylindrical motor has two phase winding. This motor has two phase winding. And there are no windings in case of the rotor. Okay, so the inductance will change when rotor moves. Okay, so inductance will change or reluctance will be changed when this rotor will change. Okay, so here the reluctance here the reluctance is minimum and inductance will be maximum. Here your inductance will be minimum and reluctance will be maximum. Okay, so here reluctance is changing. Okay, so therefore it is known as variable induction motor. Okay. So inductance very inductance is inductance of each phase winding inductance of each phase winding will vary with rotor position. Okay, so this is for windings. So they will have different inductance, and this will vary with the rotor position, and it will be maximum when the stator field axis coincide with. So this L will be maximum when this coincide with the field axis. Okay, this is. Okay, so this W salient pole has 4 salient poles. Okay, and the speed windings are concentrated like this. Okay. So now for the same frame size, the doubly salient bearing produces more torque. So this doubly salient motor. So doubly salient switch reluctance motor has more torque as compared to the singly salient reluctance motor. So mainly the single salient pole is used more. Okay, so doubly salient reluctance motor are more common. So this is the construction of the switch reluctance. Okay, so this is single salient. Here it is 2-pole rotor, and rotor have no windings. Okay, and it is the V salient pole, so it has got 4 salient poles, and windings are on these salient poles like this. Okay, and again the rotor has no windings. Okay, and for the same frame, the doubly salient reluctance motor has more torque as compared to the single salient reluctance motor. So this is very commonly used. Okay. So now we will see the principle of operation. This construction. So let's suppose this is A dash. Windings are bounded like this. So this is A dash. This is B dash. This is C. Okay. So this is 3-phase A, B, C. 3-phase 6/4 SRN. So this gives stator poles. Okay, so we have got the 6 salient poles. Okay, A, B, C, A dash, B dash, and C dash, and 4 rotor poles. Okay, so it is written like this. So 3-phase 6/4 SRN. Okay, so rotor has got 4 poles like this. 1, 2, 3, 4. Okay. So this is 1. And this. is three-phase stator pole, six stator pole, and four rotor pole switch reluctance motor. Okay. So when winding A is excited, so the rotor will attract, will align, will get aligned with this axis, which will minimum air gap, okay, or maximum, or the flux linkage are maximized with here. Rotor will rotate in such a direction, so flux linkage maximize with this. Okay. So rotor will get aligned along this axis. Okay. So when phase A is excited, so rotor orientation is such that the flux linkage should be maximum with phase A. So rotor will come in this position. Okay. And when we de-energize this A and let we energize this phase B, so now this phase B is energized, okay, and this phase A is de-energized, okay. So rotor will rotate such that it will have maximum flux linkage, okay. So this will apply or this will try to align in this axis, okay. So rotor is in this position. Okay, so which phase is energized? Phase B is energized. So this part of rotor will get attracted towards B dash, and this part of the rotor, this pole of the rotor, will get attracted towards B, winding B. Okay, so now the orientation, the rotor will rotate in anti-clockwise direction. Okay, and it will align in this axis like this. Okay. This is one and this is. So there will be clockwise direction. Okay. So when phase is de-energized and B is excited, rotor moves clockwise so as to maximize flux linkage with phase, which is phase B axis. Okay. Now, let's suppose this phase C is energized. Okay, so when say phase C is energized and B is de-energized, so this will move along the axis of C. Okay, so in this way it will move. Okay. So in clockwise, in counterclockwise direction. Okay, so when phase A is energized, okay, so rotor will align in the axis of phase A to have maximum flux linkage with phase A. Okay, then we de-energize this phase A and energize phase B. Okay, so this phase B is energized. Okay, so this rotor, this part of the pole, rotor pole, will get attracted to the axis of B. Okay, so this will rotate in clockwise direction. Okay, so this will have maximum flux linkage. This part. Okay, so here B is so it will move in anti-clockwise direction because it is near, more near. Okay, this part is far away from B. So this is more near, so this will align. So this both magnet will align in this fashion. Okay, and then when C is energized, so this part pole number 2 and 1 will align across C. Okay, so in this way, this motor will move in anti-clockwise direction. So motor rotates in anti-clockwise direction for the excitation sequence in clockwise direction. So excitation sequence is first we excite A, then B, then C, and rotor will rotate in counterclockwise. Okay, so in this way, the motor moves. So the actually the phase current to the stator are switched on and off synchronously. Okay, so this sequence, when we analyze A, then B, then C. So this is done in synchronism with rotor position. Okay. So this depends on rotor position. So according to the rotor position, we excite the phase A, phase B, and phase C. So here we require rotor position sensor. So it can be of the Hall effect sensor or electro-optical sensor. Okay, so it depends on the rotor position. Okay, so the torque production in case of this variable reluctance motor depends on the rotor position. Okay. So synchronism of switching of the phase winding with rotor position is essential for continuous rotation of the rotor. Okay. So switching, we have to do switching in such manner, so there will be continuous rotation of the rotor. Okay. So how is torque is produced? Suppose I and L is the inductance of the coil. Okay. So energy stored, kinetic energy stored in this inductor, E is equal to half I square half L I square. Okay, and if you want to find the torque, so torque is equal to dE with respect to change in rotor position. So theta is rotor position, rotor angle. Theta is rotor position. So differentiate the above expression with respect to theta, keeping current I constant, so we will get tau vector is equal to R I square B and I. So tau is proportional to I square and it is proportional to rate of change of inductance with rotor position. Okay. So this is derivative of L with respect to rotor position. Okay. So this is I square. So current is positive or negative. So it will be positive. Okay. So torque, in order to maximize torque, so we switch the current in such a manner that dL by d theta should be greater than 0 or it should be positive. Okay. So switching of the current in reluctance switch reluctance motor is done in such a way that derivative of L with respect to rotor position is always greater than 0. Then only the torque will be greater than 0 or there will be average torque produced is greater than 0. Okay, so for torque position, this condition is very important that I is switched when dL by d theta is greater than 0, then only we get torque which is greater than 0. So the current is switched, that's why it is known as switched. Okay, and there is variable reluctance, so switch reluctance motor. So this motor has to be switched at regular intervals with the rotor position. Okay, so to have optimized torque. Okay, so how we can optimize this torque expression? So we have to switch the current such that dL by d theta should be maximum. Okay. Now we see how torque is produced and why we have to switch current I when dL by d theta must be 0. And when, so let's suppose this is A, these and these, theta is equal to this. This is two-pole stator and two-pole rotor. Okay. Two-pole stator, two-pole stator, and two-pole rotor. Okay, so here in this position, theta is equal to 0. So L will be so inductance will be minimum. Okay. So let's suppose this motor moves like this. This theta theta is equal to theta. Okay, so rotor rotates in clockwise direction, and there will be a minimum air gap between stator and the rotor. Okay. The pole phase overlap and reluctance is seen to be minimum. Okay, so here reluctance will be minimum. So therefore L will be maximum. Okay. So here L will be maximum. Okay. So let's suppose initially the L is minimum, okay, and then as it is moving, it is rotating in clockwise direction like this. Okay, so this reluctance is decreasing and inductance is increasing. Okay, so this is L, so this will be increasing. So this is L minimum, and this will be L maximum. Okay. So this is theta is equal to 0, and this is theta is equal to theta. Okay. Now, so this is A, then okay. So when theta is theta 2, this is theta is equal to theta 2. So again the pole phase of both stator and rotor are overlapping each other. Okay, so there will be a constant reluctance and inductance will be constant. So this will be theta is equal to theta. So when we moving in clockwise direction, okay, so the air gap and the reluctance is constant since L will be constant. In here it will move from, it will linearly increase from minimum to maximum value, then it will be constant. Okay, like this. Now, this is C. Now B is gone out away from the stator. So rotor is gone out away from the stator. Like this. The angle is theta. This angle is theta. So again, now in this case, reluctance will be maximum. Okay. So again, reluctance, inductance will be minimum. Okay. So this will decrease the like this. This is theta is equal to. So this will come again to minimum. Okay. This will be now this one will come to here like this. This is 1 and this is 2. This is theta and this is angle 1. Theta is equal to theta 4 is equal to 1. So this will remain constant like this. So in this way, the reluctance of the inductance of the windings will change like this. Okay, of the phase windings. And after that, it will again repeat the same cycle. So when pole phase of stator, stator and this rotor overlaps or coincides, so there will be maximum reluctance or reluctance will be minimum. So in figure B and C, these are constant. From theta 1 to theta 2, it is constant. After that, it is moving away from the stator. So this is the stator. And rotor is moving away from the, so reluctance will increase gradually and it is proportional reluctance, so this will decrease like this. Okay. again same procedure will take place and will be the sign. Okay, and when you take from theta 3 to theta 4, so the reluctance remains same and reluctance will be same every. Okay, so reluctance will be maximum here and inductance will be minimum. Okay, so this is the variation of the inductance. So this is inductance variation of stator phase winding. Okay. But torque is equal to half Li square dl by dt. Okay. So we are more interested in finding dl by d theta. Okay. So variation of L is minimum when it is constant, theta is equal to 0, theta is equal to theta 1, theta is equal to theta 2, then it will decrease linearly, theta is equal to theta 3, it will remain constant, so 180 degrees, and theta is equal to theta, and it will repeat itself like this. So we are more interested in finding dl by dt. So here this is L minimum and it is L maximum. Okay. So here inductance is varying linearly. So this dl by d theta will be constant. Okay, as it is moving linearly, so this will be constant. Okay, and then this L is maximum. Okay, so for theta is equal to 0 to theta 1. dl by d theta is constant. Okay, and L is varying from L minimum to L max. Then for theta is equal to theta 1 to theta 2. From theta 1 to theta 2, L is constant. L is equal to L max is constant. So differentiation of constant term is always equal to 0. dl by d theta is equal to 0. So this will become 0. Now from theta 2 to theta 3, this is decreasing, L is decreasing from L max to L minimum. So this will increase in negative direction. Then again it is constant, so this will be 0. Again it is increasing, so this will be constant 0. Okay. So this will be the wave shape of dl. So from this waveform, it is clear the torque is proportional to S. Torque is proportional to dl by d theta. So for positive torque, T must be greater. So we have to switch the current when dl by d theta is positive. Okay. If you switch when dl by d theta is negative, so you will get negative torque correspondingly. Okay. So we always switch the current when it is on. Okay. So that's why for getting average torque positive, we always switch the current when dl by d theta is positive. Okay, so dl d theta can be positive and negative. And for negative torque, so you can switch the current when dl by d theta is negative. Okay, so this will give regenerative braking. Okay, so regenerative braking operation. Okay, so that's why we always switch on the current when dl by d theta is positive to get positive torque. Okay, so to get positive torque. Okay. So if you see, so average torque for this is 0. Okay, so this is equal to, so this is constant, so this magnitudes are equal. So if you take average dl by dt, so this will be 0. So average torque will be equal to 0. Okay, so positive value of average torque is produced when phase winding is excited. Okay. So for positive average torque, phase winding are excited when dl by d theta is greater than 0 or positive. Okay, so this procedure is followed for all stator winding in sequence so that positive torque is developed when rotor rotates. Okay. So now how to get this switching action? So switching inverter is required. Okay. Switching inverter is required. Okay. So now we will see this switching inverter. So we have this half inverter. Is This is switching bridge inverter. Which is used for switching the current. Okay. So when T is on, when T is switched on, okay. So current will flow to the circuit. So this is on, and voltage across stator winding, that is VDS. Okay. So current will flow in this direction. Okay. And voltage across the stator winding Vs will be equal to VDC, and current I will increase. Okay. Now when T is switched off, so this T is switched off. Okay. So the current will freely through this diode. So D will comes on, D is on, okay. And current will flow like this, and Vs will be equal to minus Vs. Okay, so this is across, this is minus plus when T is on, and Vs will be minus. Okay, and current will flow in this direction, and therefore I is. Okay, so when power transistor T is on, current is increasing, and when diode D is on or this is off, current is freewheeling through this diode D, or current is increasing. Let's suppose when transistor is switched on, this case Vs is equal to Vdc is equal to R is equal to and d pi by dt. Okay. This is the flux, number of turns, and this Ri is the resistive torque. Okay. So we are neglecting this resistive torque. So VC is equal to n d pi by dt, or pi is equal to integration VDC upon n into dt. For pi is equal to integration VDC multiplied by omega where we do that, and d omega by dt is equal to dt. So phi is equal to VDC omega n by dt, or VDC upon omega n. The integration of d theta is theta. Okay, and also we know that I is equal to n pi upon n. Current is equal to n pi upon n. So substituting the value of pi here, so we will get pi is equal to n upon n into VDC upon L into theta. 1 omega and we have to reluctance about. So this will be VDC. So theta is the relation. So n is cancelled n into 2D. Okay, so current in the stator winding. This is I. So I is current in stator winding. So I is proportional to theta and I is inversely proportional to L. Okay, so from this expression you can find I is proportional to theta, and for proper controlling, by proper controlling VDC, we can increase the value of I. Okay, so by controlling this VDC, we can control the value of I. Okay, so thus we can control the torque. Okay, so in this way, we can switch current when dL by d theta is positive. Okay, so by using this switching inverter. Okay. So this is all about the working principle of switch reluctance meter. So in next class we will see the mode of operation of this switch reluctance meter. Any doubt? Okay, then thank you class.